In this lecture, we're going to look at bond and molecule polarity. We're going to see that those shapes molecules take also gives them sometimes positive and negative poles, and all of that affects how molecules interact and react. We know that electrons are shared in a covalent bond, and they can either be shared equally, and that gives us a nonpolar bond, or they are unequal, and that is a polar bond. And we're going to see a lot of important things about those polar bonds. Shape and electronegativity is what helps us determine polarity. Now, for polar bond, now I'm considering just between two atoms. We're going to have an issue of electrons being pulled closer to one than the other, and you know that that is electronegativity. When that happens, it causes one to be slightly negative and one to be slightly positive. There are two ways that can be shown. I prefer the method with the arrow, but we also see a method that uses this lowercase delta, the Greek letter delta, and it puts a little positive towards the end of the bond that's slightly positive and negative towards the end of the bond that's pulling those electrons closer to itself. I like to use the arrow method, and it always points to the higher electronegativity. Higher electronegativity, I'm just gonna skibble there, you know what it is, electronegativity. So it always points, so it could point left or right, it's always going to point to the atom that has the larger electronegativity value. Remember that electronegativity is that ability to pull electrons closer. And so we do need some sort of a cutoff point, and we're going to say anything less than 0.4 is a nonpolar bond. So they don't have to have the exact same value. It can be very close. But as soon as we get to 0.4 or greater, that's going to be our magic number. We're going to say that it is now a polar bond. Well, you're probably wondering, we know a trend for electronegativity, but now she's talking about specific values. There are specific values. They're on page 263 of your textbook. You do not have to memorize these. Obviously, there's a lot of them. We are mostly interested in the nonmetals, so that cuts out a lot, but still, you don't have to memorize them. Values will be provided on tests and JIPs. Let's go ahead and dive right in and look at specific bonds and try and decide, are they polar or nonpolar? So what you're going to do is you're going to look up the electronegativity value for carbon and then the electronegativity value for oxygen. You're going to go ahead and take the difference. You're going to subtract those, and it's always the bigger number minus the smaller. And if you find that it's a polar bond, you're going to go ahead and draw it over here in this last spot, and you can choose whether you want to draw it with the partial delta symbol or if you want to use the arrow. So pause the lecture, do that, and then turn it back on to see how you did. Here I have those values from the chart in your textbook, and when I subtract, I get 0.89, so that is definitely a polar bond. We have hit that magic number of 0.4 or higher, and then as I said, I like to use the arrow. Oxygen has the greater electronegativity. You're going to go ahead now and try that for our next bond formed between Cl and P. Turn the lecture back on to see how you did. Using those values, we get 0.97, so again, we have a polar bond. And notice this is what I was saying, those arrows could go left or right, but it always has to point towards the element that has the larger electronegativity. The last one is a CH bond. Go ahead and do that one and then turn the lecture back on to see how you did. Now this one, we only have a difference of 0.35. It is a nonpolar bond, and then notice we don't need to put anything, no arrows. Please, if it is a nonpolar bond, you don't do anything to it, and that indicates it is nonpolar. Well, that was looking at bonds. What about the molecule as a whole? Because the molecule as a whole is what we're interested in. How reactive is it? What causes it to be reactive? We're going to consider two things. First, I always like to look for shape. If it's bent or pyramidal, that is automatically going to make it a polar molecule, and you don't have to do any further investigation with electronegativity. You can if you want to, but you don't have to. And then with the other shapes, Then you're going to have to use your electronegativity chart and decide, do we have essentially kind of an uneven balance with polar bonds and perhaps maybe a mixture polar and nonpolar. We do, again, as I said, we need to consider the shape. I have an example here of water. A lot of times when I draw water, it looks like this molecule down here. That's how I draw it on paper. It looks linear, but I have to consider this actually has tetrahedral electron domain geometry, and it causes the shape to be bent. And bent is one of the shapes that is always going to be polar. Not every molecule with polar bonds is a polar molecule. So we have to look more closely. Once we identify the polar bonds, do they cancel out? And I'm using an example here with boron in the center. And remember, it likes to only form 3 bonds. On the left here, it's bonded with fluorine. And when I look up those electronegativity values, the differences, I end up with these polar bonds. And it looks like they're all pulling equally away, and sure enough, it cancels out. So even though there's polar bonds, the molecule itself is nonpolar. But now let's consider if we replace one of those fluorines with a hydrogen, turns out the boron-hydrogen bond is not polar. And now I sort of have this unevenness in the molecule. The whole molecule, I like to say, sort of tilts in one direction. And this is now a polar molecule because all of those polar bonds do not cancel out. So it gets kind of detail-y once we move past the shape and have to start considering the individual bonds and how that affects the overall appearance. We're going to go ahead and practice with 4 molecules. What I'd like you to do, we're going to start with NH3. I want you to first draw the Lewis structure, and then that way you can decide from shape alone. If the shape is not the bent or trigonal pyramidal, then go to the electronegativity values and figure out those bonds, and then try and decide for the molecule as a whole, is it polar or nonpolar? So take the time to do that and then turn the lecture back on to see how you did. Here's my molecule, and I can see it's got that lone pair on the nitrogen. This does have, it looks like the tetrahedral electron domain, and it has the trigonal pyramidal shape, which automatically I wouldn't have to consider bonds, but the NH bonds are also polar and they don't cancel out. So in this case, the molecule itself is polar, and that's going to make it more reactive with other molecules. Next, let's go ahead and do the CH4. You're going to follow those same steps. You're going to draw the Lewis structure. If the shape is not bent or trigonal pyramidal, then you're going to go to your electronegativity values, determine if the bonds between 2 atoms are polar or nonpolar, and then decide for the molecule, is it polar or nonpolar? Pause the lecture while you do that and turn it back on to see how you did. Here is my CH4 molecule. The shape is tetrahedral, so that means I had to look more closely at the individual bonds, and the CH bonds are nonpolar. So because they are nonpolar, the molecule itself is nonpolar. Now go ahead and move on to the CH3F. Do those same steps. Pause the lecture while you do that. Turn it back on to see how you did. We still have the tetrahedral shape. We know the CH bonds are nonpolar, but we have this CF bond, and it turns out that is polar, and now it's not canceling out. There are no other bonds pulling it in opposite directions, makes the whole molecule polar. So even though we had these 2 that were both tetrahedral, both with carbon in the center, they both have some hydrogens, that one difference of the bond to fluorine makes the molecule polar. The last one you're going to do is CO2. Follow all the steps and determine is the molecule itself polar or nonpolar. Here is my CO2. It is one of these that has some double bonds. Now sometimes students might draw it with a triple bond. That would also be a valid dot structure. It would still be yes, yes, yes on the checklist, but experimentally we are pretty sure that the shape is with the two double bonds. We now have a molecule that is linear, and then we've got to dig deeper. The CO bonds are polar, so we might be thinking, okay, maybe the whole molecule is polar. But if I draw in the arrows for the polarity, it's like a tug of war, and there is no winner. So the molecule as a whole is nonpolar because those polar bonds cancel out. And that is our lecture on polar bonds and polar molecules.